Hey, this is Meyer. This is my Faraday's Law Lab. To start off with our introduction, the purpose was to explore the interactions between a falling magnet and a tube of aluminum foil to study the magnetic induction and currents from a Curlier-induced electric field. The fundamental principles in play include Faraday's law, saying that variable magnetic field around a loop induces a proportional but opposing voltage to change in magnetic flux. The use of art law describing the relationship between the magnetic field at a point and current, and then Newton's second law and that a system's change in momentum over time is proportional to the net force applied and vice versa. So an overview of what we did in this lab, using an experimental model observing a bar magnet falling through a conductive tube of aluminum foil and then modeling this computationally to simulate the dynamics of the bar magnet dropping through a conductive tube. Um, as a point dipole through a stack of non interacting conductive rings. And so our results, our experimental average time from our five trials is 1.476 seconds. Our computational time was found to be 1.36 seconds. So the difference between these to be 0.116 seconds. So again, going into those formulas from the concepts. So Faraday's law applies an integral due to the change or variable nature of the dot product of the induced electric field and length of the segment. So incorporating Lenz's law, the direction of the induced electric current opposes the change in the magnetic flux produced. Be it Servart law, once again representing the magnetic field as the current times the cross product of the length of the segment and the unit direction over the distance squared. So these two are used later in our computational model, and then Newton's second law, the net force equal to the change in momentum or change in time, and that's how we know or looked at our net forces in play or forces in play. And so going into that, we basically assumed that our net force was going to be mainly down because the magnet was falling through, and that's going to be the interactions assumed to be the force, magnetic force, and the gravitational force. And so our procedure, basically just dropping through the bar magnet through the tube five times, repeating and finding the average time for the magnet entering and falling through the tube. So our system was the bar magnet plus the aluminum tube and the surroundings for everything else. And those assumptions as the bar magnet as the magnetic dipole, and those only forces being the gravitational magnetic forces with air resistance negligible. Um, in terms of our initial experimental findings, so we know from lab two that the magnetic dipole moment of the same magnet I use is 3.34, the weight of 0.021 kg, and then for our aluminum foil tube, length of 0.331 meters, inner radius of 0.0254 meters, total radius of 0.0381 meters, and then the width of our foil being 0.0127. And so with our trials here, the average time was 1.467 seconds. This was our computational model, so using the constants here, and then our initial conditions that we just talked about. And then going into here, so we're setting up the magnetic field of a bar magnet formula and our change in magnetic flux. And then finally using that to model only the magnetic and gravitational forces acting upon the system here. So we have gravitational, magnetic, and then our net force. Here, just using this to update our position and velocity for the visualization of the magnet in the computational model that was shown right here of it basically falling through. And so looking at the graph that was also outputted here showing us that the gravitational force is greater than the magnetic force upon the entry and exit of the magnet from the tube, but in the middle here they seem to be essentially balanced, meaning a constant velocity or no acceleration of the magnet. In terms of the interpretation questions, we could see from, again, the visualization there that red would be counterclockwise and blue would be clockwise. Flipping the magnet, the direction of the current would be flipped, the magnetic would fall as usual. And then comparing our models, the computational models gave a time and tune that was approximately zero point 0.1 seconds less than the experimental, likely due to air resistance and the presence of other forces not accounted for in the computational model that exists in the real world. And once again, yeah, we know that the gravitational force was greater than the magnetic force at the entrance and exit, but roughly equivalent inside. If the resistivity was as close to zero, deriving from Ohm's law, we know that decreasing the resistance would increase the induced magnetic field. So this would directly impose, or current, sorry, so this would directly impose the magnetic flux and create a magnetic field that would slow the magnet's motion down. And then if there were holes, this would basically have the opposite effect of increasing the resistivity, so the magnet would fall faster. And then errors, assuming only that there was gravitational magnetic force, we know that in real life there would be aspects of air resistance, friction, and other contact forces if the magnet were to touch the side of the tube. And once again, we must also account for human error within measuring and scrubbing through our experimental trials videos for timing, because that was entirely dependent on our own measurements. Thank you.